Lecture 10, Part 3. In the previous section of these utilities lectures, we have seen that a pocket in a grand composite curve, like one it is shown here, doesn't need to be considered in relation to utilities. Okay, the excess heat within the process here, for example, of the hot streams can be used to supply heat where the heat is missing to the cold streams. Okay, and so here we have process to process heat transfer. While we are actually using this part of the hot stream or the heat available in this interval, we are using it to generate high pressure steam. And by generating high pressure steam, we can make power that actually normally we get from the outside suppliers. Okay. And from this part of the process, the heat is actually finally rejected to the cold utility, and in this case, that is cold water. Now let's look at a slightly different scenario. So we very much like our generation of this high pressure steam. So we want to actually produce more high pressure steam because it gives us more power to the process. So in this scenario, we are ignoring the process pocket that we normally have or we had in this first case. So here we are assuming that we don't have a pocket. And by doing that, we actually extended our high steam pressure generation within the pocket itself. So the heat that was used, for example, this part of the heat that was used to supply to these cold streams are now being used to generate extra high pressure steam. And by producing extra high pressure steam, we can actually generate more power because we can give this high pressure steam to a steam turbine and that can generate power. But now we are missing the heat that was actually provided by these process streams to this part of the cold streams. Okay, so as a consequence, we have to supply another form of utility, and in this case, we are supplying, for example, LP steam to satisfy the need for the process heating of this part of the process stream, the cold streams here. And in this case, actually, it is very convenient because we can generate high pressure steam and then provide that high pressure steam to run steam turbine and generate power, and then use the exhaust of that steam turbine as LP steam to satisfy the heating requirements of this part of the process. And for the remaining part, like for this part of the process, just like before, we are rejecting the heat to the cooling water. So by doing these changes, we have actually shrunk our process pocket from this size to only this size, while we are still actually satisfying the heating demands of our process. Okay. Now the question is that, so when do we not use a pocket and when do we use a pocket in relation to these utilities? So basically, we should use a pocket in relation to these utilities if the pocket spans the temperature of the utilities. So for example, here, this pocket spans the HP steam generation and LP steam use. So we can use this pocket. But if this pocket was only till here, only in this part here, then we are actually very much limited because we cannot generate steam and then use it for a steam turbine and then use the exhaust of that to a lower level. Okay, so we are then very much limited in terms of the use of this pocket. And other thing that we have to be pay attention is that what is the heat duty advantage that we are getting. Okay, so if we, for example, in this case, we are getting a heat duty from here to here, but if we are getting only a heat duty, or like let's say a marginal increase in heat duty, then it will not be worthwhile to actually make our process more complex, add a lot of equipment to just get a little bit advantage of in terms of steam generation. Okay, so the heat duty has to be significant to apply this kind of treatment. So for example, here we are actually having a significant increase in heat duty, and that's why the use of this steam, the process to process pocket is of benefit to us. Another limitation in how we use our grand composite curve and our hot utility is in the case here, for example, of these flue gases. So we said before that once the flue gases have been used for process heating, for example, in this case here, and they are past the stack temperature out, we cannot use the heat and we have to release that heat to the environment. Okay, So the temperature limitation in terms of making the use of those hot combustion gases is the dew point temperature that is shown here. And we cannot take the heat of these flue gases below the dew point temperature. Okay. However, let's have a look at this situation. So the dew point is actually below the pinch temperature. So this is the pinch here, and this is the dew point temperature. And we have already said that the pinch temperature is the limiting point where our process needs heating. Okay, so below the pinch temperature, we have a heat source, and consequently, no further heating is required at that temperature. However, from the pinch temperature down to the dew, that is the area here, we have heat that could be used, but actually it is not required by the process. So we have this available heat, but it is not part of our process. And we are still having to throw away a large part of the heat that could be recovered, but we cannot because the limitation of the dew point. So we may not always be able to extract heat down to the dew point temperature, depending on the shape of the composite curve and the location of the pinch in terms of each temperature in relation to the dew point temperature. So now what happens if we want to have two utilities supplying our process heating requirement, one of which happens to be the flue gas or possibly any other, for example, sloping utility such as the Hall-Oates circuit here, like here, for example, and a utility such as steam gas usage, for example. Okay. In our first process, we are using the flue gas to supply the heating requirement of the process, and based on the slope of this line, we can calculate, or the mass based on the supply temperature of the hot oil and the pinch temperature, we can actually calculate what is the mass flow rate of the flue gas we need to supply. Okay. We have already stated that the hotter the utility, the higher the cost. And in this particular case, we are going to use, for example, only the flue gas, so it is quite expensive. Okay. While in the second case, we have the option of using a combination of flue gas with the LP steam. Okay. And by doing that, we are actually limiting the amount of high cost utility and using a cheaper utility such as low pressure steam. Okay. And we determine with our temperature of LP steam that we are going to require this much amount of LP steam. However, the flue gas does not cease to exist at the temperature of the LP steam. It goes down to the ambient temperature, that is, for example, here, and it could be used to heat the process right down to the pinch temperature. Okay, so it cannot be used below the pinch temperature. Consequently, once we have made the addition of the LP steam for process heating, we continue to use the flue gas for our process heating in addition to the LP steam and down to the pinch temperature. So we are still using this part of our process heating by using the flue gas. Because we are already paying for it, and the mass flow rate or the amount of fuel that we are using accounts for the total, for example, the flue gas that is available down to the ambient temperature. So using this small portion of flue gas in addition to LP steam still help us to save money. By combining our flue gas with our steam or LP steam, we managed to reduce our flue gas usage that we required within this chemical process, and our flue gas is cooled right down to the pinch temperature in both these cases, in this case here and in this case here as well. Now let's talk about the cooling utilities, for example. So the refrigeration can also be considered rather like steam. As we decrease the refrigeration temperature, so the cost decreases. Okay, so if we want to make this process of cooling below the pinch temperature to be as simple as possible, we just use, for example, one refrigeration at, let's say, minus 70 degrees centigrade, as it can supply the whole amount of cooling that is required. Okay, But if you look at the process, you can see that the majority of the cooling that is required in the process is happening at -5 degrees centigrade. So consequently, we want to try and minimize the use of high cost refrigeration, that is the -70 degrees centigrade, and then replace it with low cost refrigeration. Okay, so we minimize the amount of -70 degrees centigrade refrigeration, and we replace it with some portion of -40 degrees centigrade refrigeration and a big portion of the cheapest form of -5 degrees centigrade refrigeration. So this is the optimal use of refrigeration to supply our process with the cooling that requires, and doing it at the cheapest possible cost. However, we have to take into account that supplying these three levels of refrigeration for our system is going to be much more complex, okay, than just by supplying the -70 degree centigrade utility, okay. So we have to always make a choice in terms of complexity and in terms of the cost. The total amount of refrigeration that is required in terms of QC min, for example, the minimum utility requirement would be a sum of the sum of these three utilities, the one with -5 degrees centigrade, -40 degrees centigrade, and the 70 degrees centigrade. We have also discussed previously our utility pinches. So where the utility touches, for example, the grand composite curve, we have a utility pinch. Okay, so the temperature between the utility and the cold process stream, in this particular case here, is exactly delta T min. Okay, as I explained in the previous parts, and by that definition, we are actually at a pinch point. And these utility pinches actually provide a separate design region within our chemical process, as we will see in the next slide or two. So we can show this more easily by using something what we call a balanced composite curve, that is shown, for example, here. The balanced composite curves are the same as the composite curves, but in addition, for example, to our process streams, we have add our utilities, for example, to our hot composite curve if they are the hot utilities, and we add our cold utility to the cold stream if, for example, if they are like cooling water or refrigeration. So here in the dark line, the hard line, we have our normal process stream, for example, from here to here. And then here in the middle, we have added our hot utility, for example, steam in this case. And now this is actually converted from a normal composite curve to a balanced composite curve. We can see our original pinch temperature or pinch region, and then we have a utility pinch here due to the addition of this utility. Now, in terms of the design regions, we will design in three different regions. So we will design in this region, okay, that is below the pinch. Then we will design in this region that is in between the process pinch and the utility pinch. And then we will design in this region that is above the utility pinch to the end of the process stream. Okay, so that will be our three design regions when we are talking about hand design. So we have to design a hand network for all these three regions separately. However, sometimes when we make use of our utilities with our grand composite curve, it is not so easy to determine where the utilities may touch the grand composite curve. So consequently, defining those design regions that we need for the development of our heat exchanger network may not be quite so easily seen from our grand composite curve. So in this particular case, we have, for example, to make a balanced composite curve. Like here, for example, we can see in the grand composite curve, the utility is there, but actually we cannot see that how far it is from our other utility pinch, okay? While in this case, we can clearly see that by adding this utility to the composite curve and making the balanced composite curve, we can clearly see that our utility pinch is actually far from our process pinch. and also from our use of our utility itself. Okay, so by converting our grand composite curve, or by adding utilities to our composite curve, we can actually see where different pinches lie in our process composite curves. So the composite curve or the balanced composite curves give us the complete picture. Okay, so we need to add utilities back to our composite curves to form the balanced composite curves, and to actually show exactly where our utility pinches are in relation to our process pinches. Okay, as I explained in the previous slide. So here, for example, in our balanced composite curve, we have a complex usage of utilities. For example, we have the flue gases, we have steam in our hot composite curve, and we have refrigeration and cooling water for our cold composite curve. Okay, and here is our process pinch, and then we have one utility pinch below the process pinch, and then we have a second utility pinch above the process pinch. Previously, for the case of our traditional or normal composite curves, we design above the process pinch and then below the process pinch. But now in this case, we will design, for example, above the utility pinch, that is above the process pinch, then in between the utility pinch and the process pinch, and then below the process pinch, and then finally below the second utility pinch. Okay, so we have 1, 2, 3, and 4 different sections where we need to define or design 4 different heat exchanger networks separately for each of these design regions. So again, showing in slightly different way in terms of our different utilities associated with our hot composite curve. We have the HP steam, we have the LP steam, and then we have for example, for our case of cold composite curve, we have the cooling water, and we have the refrigeration in terms of the utilities. And we have one utility pinch below our process pinch. Then we have the process pinch here in the middle, and then we have one utility pinch that is above the process pinch. Okay. In this design region, we are, for example, our hot and cold streams are out of balance, and we have to use the hot utility as HP steam to actually balance these out. So we are only using HP steam in this design region. Then we have the second region where again the hot and cold utilities are imbalanced, and to balance it we have to the hot and cold process streams are out of balance, and we have to use the LP steam as utility to balance this region. Okay, so again we are just using this utility of LP steam in this region only. And then we have another region below the process pinch and above the second utility pinch where we are actually using cold water as utility, and we are only using this cold water in this region only. And then we have the final design region where we are using refrigeration as cold utility, and we are only going to use refrigeration in this region. So we have 1, 2, 3, and 4 design regions. Like for example, in the first region, we only need HP steam as the external hot utility, and this is above the first utility pinch. Then we have the region in between the first utility pinch and the process pinch, where we are using LP steam as our second utility. And then we have the third design region that is in between the process pinch and the utility pinch, the second utility pinch, and here we are using cooling water as the first cooling utility. And then we have the last design region for our hand design, where we are actually using refrigeration as our second cold utility. Okay, so each of these utility pinches actually create an additional design region where only the most appropriate utility is used within that design region. Okay, and for each of these design regions, we have to design a separate hand network. So in terms of the summary of this lecture, the grand composite curve can be constructed directly from the problem table algorithm, as we saw in the lecture. The grand composite curve shows utility requirements both in terms of the enthalpy and also the temperature terms. Okay. The temperature differences are built into the construction of composite curves and grand composite curves, taking into account the minimum approach temperature of the problem. And these can be used as a tool for utility placement, deciding which utilities we should use, both for hot and cold utilities, and how much of each utility we should be using towards the total hot utility requirement of QH min and total cold utility requirement of QC min. Okay, and we should be using the balanced composite curve to give us a proper true picture of our utility pinches and how our utility pinches divide our heat exchanger network design in different design regions. Okay, so that is all for this part of the lecture. Thank you for your time.